Good morning once again. Welcome to the second problem in the HR diagrams. In the previous problem, in the first problem, we looked at how to interpret the HR diagrams. Where does the main sequence star lies? Where does red giant star lies? And then what happens when a star transits from a main sequence to the red giant or its supergiant? Let us look at the second problem. So to understand more about it, there is already a theory which has been uploaded. You can look into it. Okay, now let us begin with this. The diagram shows the grid of a HR diagram on which the positions of the sun and the other four stars A, B, C, D are shown. Okay. So before I continue, this question is taken from 2003 March paper HL. It's in paper 3. Right. Um, so A, B, C, D are the four stars which has been shown. Sun is at this point, and this is a plot of temperature versus luminosity. Temperature along the x-axis, luminosity along the y-axis. Okay. State alternative labeling of the axis. What other labeling can we have here? Okay, if you remember, in my previous theory part, you had seen, so what is a HR diagram? How many different axes can we have? Okay, so let me see whether we have here. We don't have it in the diagram. You can see, so you can either have on the x-axis the temperature, or you can have spectral classification. Spectral classification along the x-axis. You can write along the x-axis, it is spectral classification, and along the y-axis, you have luminosity. Here you can also have absolute magnitude. These are the two alternative axes that you can have. Okay, now let us move on to the next one. Complete the table. Star A, what kind of star? Star A, where is star A? Star A is here. So first what we do is, what is known to us? Okay, we will write down the main sequence stars diagram. It looks like a S. So I'll start from here, include my sun, and include this D also here. So this will be my main sequence. So correspondingly, A and D will form the main sequence star. So let us write down wherever A is here. So I will write this as my main sequence star, and this will also be my main sequence star. Now I need to know B and C. Where is B and C here? B is at the top. What do you call this as? This was your red giant or red supergiant. You can say red supergiant because it's much more at the top here, right? If it was somewhere over here, you can say red giant, and if it is at the top over here, it is red supergiant. This is red supergiant, and what is this here? This will be your white dwarf. This will be your white. Okay, so let me write it down here. So this would be red giant, red supergiant, and this would be your white one. This will be a white one. Okay, and next is explain using information from the HR diagram and without making any calculations how astronomers can deduce that star B is larger than star A. Star B is larger than star A. Where is star B? Star B is here. Star A is here. Okay, see this super giant we already know. Okay, it is larger, but how do you deduce it is a question. What we do is, let us find out the luminosity of this. The luminosity here is given by 10 power 6. Okay, let me write down. LB is equal to 10 power 6. What all information we can get? Let us take all those. LB equal to 10 power 6 times L0. Okay, because luminosity of sun, in terms of that they have given. And then what else do we know? Temperature. What is the temperature of the point B? 5000 Kelvin. Temperature TB is equal to 5000 Kelvin. From here, can we determine the value of A? Area, because if you know, when the surface area is larger, star is bigger, right? So therefore, let me write down AB. Okay, now we know that the intensity is given by sigma A T power 4. Okay, this is what is known to us already, right? And so this is power here, not intensity, is power over here. Power is equal to so much over here. So thus, I want the value of area. Area can be written as L divided by sigma T power 4. Okay, this is what I have. This I'll write this as AB here. Similarly, I'll do the same thing for C also. For C, what do we have? Luminosity LC is equal to, now this is 10 power minus 2, 10 power minus 3. I'll make it approximately around 10 power minus 3 here. 10 power minus 3. And temperature, what is the temperature here? This could be around 20,000, 10,000, 20,000, 25,000. So TC could be around 25, 20,000, 20,000. So therefore, I'll write AC is equal to LC. Let me write on the formula. LC divided by, this was what? AB. This was by T. So much? LC divided by sigma T power 4 TC to the power of. Now you see, for AB, for the star B, luminosity is higher, area should be higher, and this value of T is lower. Value of T is 5,000. So definitely this AB is really higher as compared to AC. Why? The reason is because you see, for AC, luminosity is very, very lower. How much it is lower? It is of the order of 10 to the power of plus 4 times that of this C. So it's lower. And this TC also you see, this is around 20,000 K. See, numerator is increasing, denominator is decreasing. Here, numerator is decreasing, denominator is increasing. So what does it tell you? That AB is less than AC. Very clear indication. Okay, which also tells you when AB is less than AC, what does it mean? That means the surface areas are lesser, which means the force is also lesser, right? So sorry, not force. The what you call the size is also lesser. From here, so what we can say, explain. He's asked about explain. You need to explain over here. So how do I explain? No calculations over here. You can now say LB is greater than LC, then PB is less than TC. Okay, and then since A is equal to L by sigma T power 4. Okay, what we can say? We can say this implies AB should be less than AC, which means the size of B is less than size of C, where A is the surface area of the star. You need to mention this clearly. Okay, because this is something which you are inferring. Okay, because the moment I say A, it can also refer to this area, right? So you should very clearly mention this. Then next. Now let us begin with this. Using the following data and information from the HR diagram, show that star B is at a distance of about 700 parsecs from the Earth. Okay, apparent visual brightness of the sun. What is this given here? This is value of B is given. Okay, how do you relate B and L? You can write B is equal to L divided by 4 pi d square. What is L? Luminosity of the sun. If this is for sun, this is also sun. L sun over here. 4 pi d square. What is this d square over here? D square should be d sun square. Okay. Now visual brightness of star B. Now this I'll write this as B, something like this over here. And here next what I can do is I can write here also visual brightness of star B. So I'll write BB is equal to LB divided by 4 pi dB square. I am applying the same formula. Mean distance of the sun from the earth. What is this? This is nothing but your D0. This value is given to you. What is being found out? dB should be found out, right? Now let us start working on this. Now 1 parsec value is also given. Okay. Now we need to convert it into PCs only. Okay. Now what we need to do is we have P sun. So we need to find out the distance of this star B. That means this should be my subject over here. D should be my subject. So what I will do is I'll write L sun is equal to B sun 4 pi d sun square, and LB is equal to BB 4 pi dB square. I'll write like this, and I will divide one with the other. Okay, I taken from this formula, right? And I will divide one with the other. When I do this, this 4 pi and this 4 pi goes away. Okay, maybe I should have taken this one upwards. Anyway, doesn't matter. Now L sun, I will take this as L sun only. L sun and LB. What's the value of LB? Let us find out what's the value of LB here. We already got the value of LB from the HR diagram. Where is it? LB is here, which is 10 power 6 times L sun, right? I will write this as this is 10 power 6 times L sun is equal to B sun. What is B sun? B sun, apparent brightness of the sun is 1.4 into 10 cube. I will write 1.4 into 10 cube into d sun square. What is d sun square? D sun is mean distance is 1 astronomical unit. 1 AU divided by, okay, 1 AU square divided by now what do we have? BB. What is BB here? Which is 7 into 10 power minus 8. 7 into 10 power minus 8 into dB square over here. Okay. Now let us do this. This L0 goes away. Let me take the reciprocal. Okay, that becomes easier for me. So 10 power 6, I had 1 by 10 power 6 here. I take reciprocal here, and this will be 10 power 6 is equal to 7 into 10 power minus 8 into dB square divided by 1.4 into 10 to the power of 3 AU square into AU square. That's what I have. Okay, I'll just write this. Reason is because I need the units over here to properly mention. Now what do we have here? You have 7. Okay, let me take up my calculator to find out what are these values. Towards it, put it over here. I get 7 divided by 1.4 will be 5. This is 5. So let me write down. This is equal to 5 into 10 power minus 8. This comes upwards is 10 power minus 11, and this is dB square, and then this will be 1 AU the whole square. I can write like this. Next, what I will do is I will take dB square as a subject. dB square is equal to, and I'll throw all of them outside. That's it. Okay, cross multiply. This will become 10 power 6 into 1 AU the whole square divided by, it will be 5 into 10 to the power of minus 11. Okay, now let us solve this equation. When I do this, what do I get? 1 by 5 is 0 0.2. 0 0.2 into this goes upwards, it becomes plus 11. Plus 11 plus 6 is 10 power 17. 10 power 17 AU the whole square, which would be 2 into 10 power 16 AU. What is this? dB square. I want to get the value of dB, which would be root 2. What is root 2? 1.4. 1.4 into 10 power times AU. 10 power, this because this is AU square, right? Square goes away, I get this much. But now he is asking you to find out how to show that it is 700 parsecs. I need to complete it. Okay, so I need to express it in terms of parsecs. Now what is being given here? 2.1 into 10 power 5 AU equal to 1 parsec. But I have everything in AU. Now what I will do is, I have no space anyway, I will write it over here. I will mention, I have to mention it in parsec, right? So what is that we have here? We have 2.1. Okay, I'll write down. I will write here 2.1 into 10 to the power of 5 AU equal to 1 parsec. Then 1.4 into 10 to the power of 8 AU will be equal to 1.4 into 10 power 8 divided by 2.1 into 10 to the power of 5 parsecs. Now let us calculate this also. So this would be 1.4 divided by 2.1 will be 0.666. 0.666 into, this is 8, this is 5, this becomes 10 power 3, right? 8 minus 5 becomes 3, which should be nearly 666 parsec, which is nearly 700 parsecs. Okay, so we have got this. That's what has been asked here, right? Because it is a distance of about 700 parsecs. So we have got the answer. Next, and then explain why the distance of star B from Earth cannot be determined by the method of stellar parallax. Why can't you use stellar parallax to do it? Why do you need to go around about turn like this? The simple thing is that you can use stellar parallax only when the distances are very, very small. Okay, but the distances of the order of 700 parsec, okay, this is too much big. So as a result of it, you cannot use the stellar parallax method. Okay, so what you have to write here? You have to say distance of the star is higher, is very high, very large, and hence the angle made would be very, very small, very small. Hence stellar parallax cannot be used. Cannot use. Okay, so a lot of clumsy things over here, but anyway, I'll just put a boundary here. No, that's fine. Okay, so this is what is the reason that could be written. So with this, we come to an end to this particular problem. Let us see the next problem in the next video. Thank you.